Video lesson for chapter 6, starting with section 6.1. We're going to be talking about similar polygons, very closely related to congruent figures that we've done in the past, but this time similar, meaning their corresponding angles are congruent. We already know what corresponding angles are. It's if this angle is here and this angle is over here, they correspond with each other. They have to be congruent. They have to maintain their size, but their corresponding sides are proportional, meaning if it's shrunk down a half as big, then all three sides, if it were a triangle, are half as big as the original. Maybe it's a quadrilateral and all four sides are a third of the size as the original. Or maybe it's a pentagon and you stretched it out 4 times bigger. That's what they mean by the sides are proportional. They all have to fit. The scale factor, vocabulary word, is the ratio of the lengths of two corresponding sides. The ratio of the lengths of two corresponding sides. So many times we'll make a fraction out of it, but we could also make a ratio out of it in the sense of maybe the first polygon is 3 times as big as the other one. Then it would be 3 to 1. Or you could write it this way, 3 to 1. Now that doesn't count as having to be reduced technically because you need a scale of 3 to 1. A similarity statement looks almost exactly the same as a congruent statement, but check out that similar symbol. Remember that a congruent statement has an equal and then the swirl. This one has just the swirl. So that is similar, meaning they're very, very close. It's just either expanded or shrunk. So if you're given that similarity statement without a diagram, I don't even need a picture of these two quadrilaterals. I know the angles that are congruent. If I look at the order up here, I have angle K and angle P. So angle K is congruent to angle P. I know that angle L is congruent to angle Q. I also know that angle M is congruent to angle R, and I know that angle N is congruent to angle S. So I've got all 4 of them listed, and please notice that I kept K, L, M, and N as the first angles in the statement. P, Q, R, and S are the second angles in the statement, staying consistent with the order given up there. Proportionality statement looks a little bit different. The proportionality statement is we have to pick 2 sides that are proportionate to other 2 sides. There's going to be, well, technically 4 sides on this. Let me rewrite this down here so that I can scroll. You're going to say that the measure of KL relates to PQ. We're going to make our fraction out of that. However big KL is related to PQ, that's the same fraction or scale factor as we learned on the other page. Same scale factor as LM is to QR. That's the second side. But MN is going to be related to RS, and KN or NK is going to be related to PS. Now notice I just didn't pick any random letters. I went in order, K to L to M to N back to K. And the reason for that is if somebody draws a quadrilateral, any quadrilateral that looks kind of like a parallelogram, and it goes K, L, M, N, you have to write it in order that it's written here, K, L, M, N. You can't go K, L, M over there, N up here. Once you start at a vertex, it has to go in order, either direction. So I have my first side is KL, my second side is LM, my third side is MN, and my fourth side is KN. Oops, fourth side. Same thing over here with PQRS. So PQRS would be in the same order. If it helps to draw it, go ahead and draw them both so that you can see which sides are proportional. Please don't get mixed up which one is which. A proportionality statement actually has proportions. A similarity statement has the similar symbol, like it was written up here. Similarity statement, proportionality statement. Proportionality statement has proportions in it. All right, so here's a diagram. Pause the video if you have to draw it. Comparing polygon A to polygon B, it wants to know what the scale factor is. If these two are similar, exact same size, only shrunk, look at their angles. Their angles are all congruent. Sides are definitely not congruent. If the sides are proportional, then the scale factor of A to B, you can pick a side. Go ahead and pick the 9. 9 is going to go over 6. 9 to 6. But scale factors are always reduced. Always, always, always reduced. So this would be a scale factor of 3 to 2. Now you can check and make sure that they're similar by doing other problems. We could compare 12 to 8 also. 12 to 8. Divide them both by 4. 12 to 8 reduces also down to 3 to 2. We can't, of course, do the 14 and the y or the x and the 4 because they're variables. So if you're comparing A to B, it's 3 to 2. If you're comparing B up to A, it went from 2 to 3. The scale factor went from 2 up to 3 times as big. This one went from 3 down to 2. So scale factors are basically a reduced ratio. If you would have written them like this, that's perfectly fine as well. Doesn't matter the format. So find x, we can find x now knowing that all sides are proportional by saying our scale factor is 3 to 2. And now it would probably be easier to write it as a fraction rather than a ratio. 3 to 2, make sure you stay in order. If this is 3 times as big as twice of that, then you would also go x over 4. You have to go a over b equals a over b. Keep this polygon on top, b polygon on the bottom. You remember how to solve a proportion, cross multiply. You get 2x equals 12. Divide them both by 2, and x equals 6. Go ahead and put a 6 up there. You can check your answer. Does 6 over 4 reduce to 3 to 2? Yes, it does. Then it says find y, so we're going to use our 14 and our y because those are in corresponding positions. Same ratio, 3 over 2 equals 14 over y. Cross multiply, you get 3y equals 28. And y equals, leave it as a fraction. Unless it's a super nice short terminating decimal. If you take 28 over 3, that's not a nice terminating decimal. And no, we don't put 9.3. So 28 over 3 is just how big y is. If it reduces, reduce it. All right, real life example. You've got this swimming pool, and it's surrounded by a concrete patio. You want to know the scale factor comparing the pool to the patio. So if I compare the pool to the patio, I would say, well, the pool is 36 feet wide. The patio is 48 feet wide. Reduce that by dividing them both by 12. And you find out the scale factor of the pool to patio is 3 to 4. What are those other numbers for? To check your answer. Make sure it's all proportionate. 18 to 24. Pool to patio. Reduce them both by dividing by 6. And you still get 3 to 4. So the scale factor of the pool to patio is 3 to 4. Every 3 of those would make 4 patios. If you reverse it, patio to pool, you don't have to rewrite everything and try to reduce again. Just reduce your reversed ratio. The pool to patio to pool is 4 to 3. Then when you look at this, you know, oh, yep, the patio is bigger than the pool. If you look at this, you say the pool is smaller than the patio because they wrote it that way first. You have to make sure they're in order or the scale is going to be wrong. The scale factor of the perimeters, watch this. We're gonna go long cut and then shortcut. If you're looking for the perimeter, you would add up all of the pool, 36 plus 18 plus 36 plus 18, or 36 times 2 plus 18 times 2, and you find out that it's 108. Then you do the same with the pool, 48 plus 24 plus 48 plus 24, or 48 times 2 and 24 times 2, add them together. 108 over 144, check this out. Divide them both by 36. 108 divided by 36 is 3. 144 divided by 36 is 4. The perimeters have the same exact scale factor as the sides. We could have saved ourselves a lot of time. Instead of adding, reducing, we know that the scale factors are actually the same for the perimeter and the sides. Let's see, is that it on that page? Okay, next up, what is the scale factor? So they're asking us, what is the scale factor of the perimeters of these two quadrilaterals? And you're looking at it, and these two quadrilaterals, we don't know what the perimeter of this is, because J to K to M, we can't guess how big these sides are, and we can't guess how big these sides are. But the scale factor of the perimeter is the same as the scale factor of the sides. So pick two sides that we know. 10, oh, no, not 10 and X. The only two corresponding sides we know are 15 and 6. So if you say it goes from 15 to 6, reduce that down, divide them both by 3, the scale factor is 5 to 2 of the perimeters. It's also the scale factor of the sides. Sides and perimeters are the same. Find X, go back to the proportion. You don't have to use 15 and 6, you might as well use the smaller numbers. 5 to 2. The ratio is 5 to 2. That means this ratio is 10 over X. Cross multiply, you get 5X equals 20, and X equals 4. Or for many of you, you can do that in your head. 5 times 2 is 10, 2 times 2 is 4. So X equals 4. Write the similarity statement very, very carefully. We've practiced these with congruent statements on triangles. I'm going to go JKML. JKML. You could have gone JLMK. You could have picked M and went MLJK or MK. As long as you go in order, you can't pick L and then go to K and then down to M and then over to J. It has to go all around in order. So JKML is similar to, and then make sure this one goes in order, R, S, P, Q. The J and R have to match the K and S, the M and P, the L and Q. All right, last couple vocabulary words. A dilation is a transformation, so we're changing something, transforming it, that preserves the angle measures. Angles don't change. And results in an image with lengths proportional to the pre-image lengths. So a dilation is all this same stuff that we've been doing. It has, the lengths are proportional, the angles are the same. Here would be triangle FEG, similar to triangle FDH. And if I scroll down, I can show you that. Looks like this. Describe the dilation that moves triangle FEG onto FDH. Very closely related to a scale factor, but how does FEG get onto FDH? Notice it goes from 5 to technically 20, because FDH is the length of that is 20. So 5 to 20, what is the scale factor, or not scale factor, I'm sorry, the dilation of that to get from here to here? Describe the dilation. It is 4 times. the dilation is 4. 4 times as big. If you multiplied this times 4, it would get that large. Describe the dilation that moves triangle FDH onto triangle FEG. That means it's getting smaller, and it has to be in the same ratio. That would go from 1 to 4. If you took triangle FDH and multiplied it by a 4th, it would shrink down to triangle FEG. Notice angles are the same size, it's just the sides that are changing. All right, that's it for section 6.1. Good luck with the vocab.